is this true? Now, what did you say a minute ago?
Absolute. Oh.
It's like,
So, yeah, it's like it should be the absolute value. So it's not true as it's written. Another way of talking about this is so the answer to is this true? I'm going to say not always.
half of the time.
I mean, it's about half of the time, right? Statistically, it would be about half. And so, on what interval is this true? Because now, I mean, we want to think about functions and inputs and outputs. Our x's are our inputs. And we do some stuff to that. And so let's think about on what interval, what input values this is absolutely true for. Is it true for 0?
Yes.
Or positive.
For positive values, right. So whenever x is bigger than or equal to 0, or we could say whenever x is in the interval 0 up to infinity, like that, then yes, that'll always be true. Okay? So, another way of thinking about this, right, is if we had some function. In this case, we're going to take f of x equals x squared. Here's f of x. It looks like this. Now, this is what we're going to do. We're going to plug something into f of x, and to be explicit, yes, this is x squared. You're going to plug something into f of x, and out pops 4. What was my original input?
2 or minus
2 or minus 2, right? Now, think about this. Let's think about the mechanics of this right here. So, like, we took some number, plugged it in, okay? And out popped a 4, right? So what we're very used to doing is if you have an equation and you have something like this, you take a square root. In other words, you do the thing that undoes whatever this is. That happens to be square root. And at this point, I should have drilled it into your brains that every single time you do this, plus minus, right? Because there's 2 possibilities. In other words, that's not the full picture. By just this right here is not the full picture. Because you can't be sure that what comes back is what you originally started with. It might have been the case that I originally plugged in a -2 and then out popped a 4. Square root doesn't know anything about that, right? And if we're just talking about the square root function, it's the thing that undoes square, but it's only going to give you, like if I say, okay, the output of x squared was 4, and I say, okay, well now I'm going to plug that into square root, it's going to give me 2 every single time, right? It's always going to give me a positive value. It's always, in other words, if this is the output, then what square root is going to do is going to pull back this guy. He's going to pull back a positive number. I'm going to be using the terms push forward and pull back many times during this lecture. And when I say push forward, what I mean is we're taking some input value and plugging it into a function. And you can imagine that you're pushing it forward, right? You're taking your number, pushing it onto another axis. Then if we want to go and pull that back, find out where we came from, right? Then that's what I'm talking about. Now we're going to do the inverse to pull back a value, okay? So, for instance, if I took f of -2, well, that's just straight up 4, and then I took the square root of it. So now we're coming back to this. You see what I'm saying? This is the same thing as saying, well, you took -2 and you squared it, and then you took a square root. Well, -2 squared is what?
4.
Positive 4. So as far as square root's concerned, he's going to always assume that the thing that you gave him was a positive number. Okay? Then we have to use our brains and say, well, wait a second, hold up. And usually it comes into context in the problem, right? Like for instance, maybe 0 on the x-axis corresponds to midnight. And you know that something happened and you got 4 units of crickets and you wanted to know when that occurred, and so you say, at 2, but you know that it occurred last night, or you know that it occurred before midnight, then you'd say, yeah, hold up. But in the context, it must have been -2. As far as square root's concerned, he could never tell you that. Square root does not know. Anytime anything gets pulled back, if it's 9, square root's going to pull back a 3, right? And so on and so forth, and blah, 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 blah. Okay? Now, one second. And so, yeah, just to notice here, right? This is the same kind of thing, just from the very beginning, right? You took some number and you squared it, and it's not always the case that what comes back, because we took -2, -2 is not the same thing as 2, and so it's not going to work for every single value, which we've already puzzled out. As long as it's positive, it's going to work. But when it's not positive, it's not going to work. Okay? So yeah, if you knew ahead of time that the input was negative, then that would be enough. Okay? So another way of looking at all of this. Remember how last year, when we talked about inverse functions, we said that what you're doing is you're swapping the role of x and the role of y, and it's not simply, you don't just rotate that guy down, because if you do that, then x is pointing down, right? You want to rotate it so that x is coming up and that y is going in that direction, right? And so what you do is you flip this guy, and you end up with this image right here. Now here's the question. Here's something. Is it a function? No. No. Why?
Because every input has 2 outputs.
Every input except for 1, except for at 0. But
The 1.
so you plug in any value here. So now here are your y outputs, your old y outputs, and here are your old x inputs. But now we're swapping the role. So it used to be the case, you plug something in, you get out a 4, and now we want to say, well, you got out a 4, where did it come from? We're going to plug a 4 into this. Well, now you have 2 options. And so by definition, that's not a function. But what we could do to fix that is to notice that if I just chop this off right here, if I forget about the negative ones, and then maybe use my brain to figure out whether or not it was positive or negative or whatever I have to do, as long as I chop that off right there, that's a perfectly good function. And so that's basically what we do here. We say this right here would be the square root of x. But actually, look at how I've labeled it. It would be the square root of y equals x. So that when you square it, right, square both sides and you end up with this right there.
Yeah.
Right? Okay? And yes, usually what we do is once we get this, then we swap the roles and stuff like that. We're not going to do that today. I'm going to suggest we don't do that anymore. You'll see. So this is where we're going today. Now, it used to be. So you plug something into x squared and out pops a 4. How many possibilities were there for inputs? 2. There were 2 possibilities, right? Because again, just by the way this thing looks, we look at that and see it could have been 2. It could have come from 2 different places. So now let me ask you a different question. All right. There we go. Oh. So, this, my friend, is sine theta. Thetas are my inputs, and we'll call them y's, I guess, or our outputs. I plugged something into sine. Out popped 1/2. How many possible answers, or how many possible things could it have been that I plugged out? Infinitely many.
Oh, yeah.
But here's the thing, right? We know it had to have either come from here or it came from here, right? And you remember doing this, right? You have some trig function equals to some number. And now you want to say, well, how many possible ways will we call that? Or I guess we're going to call it there's a theta 1, there's a theta 2. If we move our way back, we could call this, I guess, theta 3. Another possibility is that it came from here, theta 4. And we keep going on and on and on and on forever. Okay.
So you can't.
But for one period.
Well,
So if there's no.
we're gonna get creative here. We're gonna try to figure this out. What we want, our goal, is in the same way that we were able to look at the inverse of x squared and say, hey, look at that. If you restrict the range here, if you just kind of forget about this bottom half, you get a perfectly good function. That's perfectly usable.
It goes on.
Well, we're gonna have to look at this and figure it out, aren't we? So here you go.
That's where we rotate it.
Oh yeah. Okay, so the first one right here, guys, orient it like this. And I would like for you to draw, just like I've drawn here, and try to draw it well. In fact, before you start drawing, I'm going to go ahead and show you some major points here. I want a few things labeled. First thing let's label is how about the theta axis. So this is going to be theta inputs, right there. And let's call the outputs y. So there's y. Now we want, on both sides, I want a full period of sine. So I'm going to try to make it end right about here. I'm going to go, that's about half. Half of that is right there. Half of that is right there. And I don't want it to be too small. I want to have some room here. So I'm going to go up to 1 right here and down to -1 there. So of course, this does not have to be perfect. But I do want this to look somewhat nice. And now once you've done this part here, okay, again, it does not have to look this good. Just try to make it look decent. I'm going to do the same thing over here with half, half, and half. This guy comes down to -1, comes up, comes down here, goes up to here, comes up to +1 here. And now I'm not going to label every single one of these points on the theta axis, but I do want a couple of them. I want to label this one right here at pi/2. I also want to label the one here at -pi/2. You should know how to label every single one of these, but that's what we're going to do. We're going to stop right there. Let me know when you guys got that picture.
But we're just doing pi/2.
Yeah, just label that. Just these 2 points here labeled on the theta axis, and the points 1 and -1 labeled on the y-axis.
Okay.
All right, you got it?
Yeah.
Okay, everybody got it. So now what we want is to see what an inverse sine function would look like. It used to be the game. Oh, and let's label it up here at the top right. Let's go y equals sine of theta. So y equals sine theta. The game used to be, you give me an angle theta. I plug it in and tell you the output y. So for instance, you gave me a pi/2. I took pi/2, plugged it in, and out popped a 1. So now what we want is the thing that undoes that. We want something where now I want to be able to plug in a 1 and it comes back to pi/2. In other words, I want to swap the roles of inputs and outputs. I want my inputs to be my new outputs, so they need to go vertical. I want my outputs to be my new inputs, so they need to be horizontal. The only way to make that happen is to flip it just like that. Now what I'd like for you to do.
I can barely see.
You can barely see yours? Yeah, because it's like pencil. Well, then maybe just watch what I'm doing here, and you could do this on your own time. I do suggest that you actually do this. But let's just watch what I'm doing here. So this was the old y-axis. And actually, you know what? No, give me a second. You guys want to use some markers. Might make your lives easier. Here, use a marker. And just do it real quick. This doesn't... Oh, ah. You got... Yeah, okay.
So just trace it.
Just trace it, yep. Just trace the front. But don't go to the back just yet. Once you get the front done, let me know.
It's most.
All right, so now let's take a look at this. Here you go. Yeah, okay, now flip yours over so you can see the stuff. Flip it the right way so that your positive y is off to the right and your positive theta is going up. Is that thing a function?
Not at all.
Not even close, right? Because, I mean, and it doesn't matter where you are. It used to be like with x squared, there was at least one point that was good. Now, no matter where you are here on the domain of the inverse must be from here to here. Right? Right? Like, because think about this. Think about this game that we've been playing, right? We say, okay, the output was a 1, and so it must have been this. I can't say, well, the output of sine was 7. No, it wasn't. It was never 7. That never happened. You're a liar. And get out of my house. You know, like that's just not going to happen. The only way to play this game is if somebody gives you some theta and something pops out, like what I originally said, like 1/2. If 1/2 pops out, well, then you have some possibilities. But if you say like 7/5 pops out, well, that's way up here. That can't happen. And so when you're talking about the inverse function, well, then it doesn't make any sense to throw in anything outside of -1 to 1, right?
Yeah.
Okay? So here's the problem, though. This thing is obviously not a function. And so in the same way that we did with, whatchamacallit, the other one. What's this one called? X squared? Yeah. And we did with this, we said, you know what? This branch is a perfectly good function. For every one input, there's one output. That's good. This messes up my life, so let's just get rid of the part that's messing up my life right here.
Or you could get rid of it.
You could get rid of you could get rid of the top part. No problem.
You just have half a period.
Yeah, interesting, right? So what we could do, anywhere along this, we could, if we wanted to, we could go up here or whatever. But pretty obvious place to start would be right here at the origin. And then just work your way out and say, forgetting all of this other stuff up here, is that a function? Yeah, it's a function, until it gets to here. Then it bends back on itself, and if you include that little part, it's no longer a function. So, we're going to go from here, work our way up until we get to here. I'm going to make a nice dot right there. And then say we're going to stop. Because if we go any further, we're going to end up with 2 outputs for some one input. We don't want that. Now we do the same thing on our way back, and we say, okay, you know what? We'll include all these guys, and we'll stop right there. And so just like...
It's a small function.
It's small, but it's going to be very helpful. So this used to be the case that I'd plug in a pi over 2, I'd get out a 1. Now it's the case that I plug in a 1 and I get out a pi over 2. Used to be the case that I'd plug in a negative pi over 2, get out a negative 1. Now I plug in a negative 1 and get back my negative pi over 2. And all the rest of this we're just going to forget about. This is what we call, we have a few different names for this. It is the inverse sine function. But it has a special name called arcsin. Arc, A-R-C, arcsin. And there's a couple different ways we could write it. But this is what it looks like. up like this. You plug in a 1, you get out a pi over 2. Comes back like this. Plug in a negative 1, you get out a negative pi over 2. And now I'm going to keep the labeling that we did before. So this is now theta. And what's nice about this is as you look at this, pi over 2, is pi over 2 an angle? Is that how we've been thinking about pi over 2 this whole time? Yeah. Is theta the name for angles? Yeah. And this makes sense because sine is the thing that takes in an angle and gives you back a ratio. That's one way of thinking about it. It gives you back a ratio. And so this is the thing that takes ratios that are in magnitude between 1 and negative 1. Because that's what sine did. Sine took any angle and gave you a ratio that was somewhere between negative 1 and 1. And so this is the function that takes ratios between negative 1 and 1 and gives you back the input angle. And so it's like I said, and so here's one way of writing it. Imagine that, right? Like F inverse, right? Just simply sine inverse.
Is that the button on the calculator?
That's the button on the calculator. Now, so this is theta equals inverse sine of
Couldn't
y.
that also mean sine to the negative 1?
No.
But you write the exponent there.
Yeah, this is what's very tricky about this. And one of the reasons why I don't like this is because I prefer to call it arcsin.
Sine to the negative 1 means...
Yeah, I know, right? Isn't that annoying? Because you think, oh, sine to the negative 1 of 1/2, then you think, oh, to the negative 1. 1 over sine to the 1/2. That's not what it means at all. This is not what that means. It has nothing to do with that. It's just that this is what we use for the inverse, right? This is the notation we use. And so you'll see it like that. It has nothing to do with 1 over that thing. This means the inverse sine. I will almost always call it arcsin because it is a function in and of itself, right? It is like, and we don't want to confuse inverse sine with cosecant, right? So this is what this is. It's defined from negative 1 to 1. You cannot plug in anything bigger than that. Because it doesn't make sense. Because remember, this is, an inverse is the other game. We're trying to pull back an output, right? So as long as your outputs were from negative 1 to 1, then it makes sense to say, yeah, sine popped something out right here. It came from here. And that's exactly what this does, by the way. If we want to know 1/2, first off, here in the first quadrant, what input gives me 1/2 as an output?
Pi over 3? Wait, no, pi over 4.
Nope.
Oh,
The other one.
pi over 6.
Yeah. Plug in pi over 6 into sine. And let me just make sure that I'm not full of it. This is pi over 6. 1 to root 3.
Yeah.
Yeah, so sine is opposite over hypotenuse. So yes, okay. So it used to be the case that you take sine and you plug in a pi over 6 and out pops a 1/2. Now it's the case, you plug in a 1/2 and out pops pi over 6. Okay? But, uh-oh. Let's see, pi over 2. Another one, how about 5 pi over 6? Ooh. Plug in a 5 pi over 6.
Wait, you
I think that's just into here. Just take sine, and plug in 5 pi over 6, and what do you get? A half. It's still half. But now take that and plug it into here, and it tells you, oh. So it's only going to give you, basically, and this is how I think about it, we're going to do this a lot. Anytime you're working on one of these, right? And you say, I have some number, I'm trying to find the inverse of it. What you could think about is, it could have come from any one of these, right? And so, let's say it actually came from this one, whatever that angle was. And so what I imagine is this. It gets pushed forward lands on 1/2. I then use arcsin to pull it back, but the thing it's going to give me is this
So you have
angle.
to like
So
subtract
then you're
pies.
going to need to use your brain and figure out, well, if I know it came from over here, if that distance is pi over 6, that distance is pi over 6. Or, you know, or if it's from over here, it's going to be a little bit different. We'll get into all the ins and outs of that. But this is a good way of thinking about it, right, as we're starting to get to know these guys. So this is another picture that you will certainly have a quiz on. Certainly. Like it's going to happen. Okay, let's see if there's anything else I wanted to say about that. Okay, yeah, then I said all that stuff. So yeah, you plug something in to sine. Out pops a 1/2. Just like before, you plug something into x squared and out pops a quarter, or out pops 4. And we say, well, there are a couple possibilities. If I just plug it into my function, I'm going to get this 1 that's over here on the positive side. But it might be the negative one. Now this is a little different. It's like I plug something into sine, I get out 1/2. And so when I pull that back, when I take the square root, like in our analogy here, then I'm going to get pi over 6. But it might not have come from there. Just like when you take a square root of 4, you get 2. Well, it might have been another one. And that's why you need to use your brain and figure out in the context of the problem whether or not this happened in the first day or the second day or whatever it was. Right? Is that making sense?
Yeah.
This is probably one of the hardest things that we're going to do this year, because this is a mind breaker. This will definitely melt your brain. Okay, we're going to do
Cosine.
cosine. Okay, and we're all going to do it together. So same deal, right? 1 or 2 full periods of cosine going to the left and the right. And let's label it and all that good stuff. So I'm going to label the input axis as theta, output axis as y. So here's theta, y, up to 1, down to -1.
Yours looks a lot better. And which ones are we labeling?
Now, good question. It says we're going to label this one right here, the pi over 2, and the pi. Because again, we are going to restrict this guy. He's not going to do us any good if you, as a function, if you plug in a number and get infinitely many outputs. So we're going to have to restrict this guy. Once you got this picture, let me know.
Doesn't look that good.
Well, I have some practice.
Accidentally did 2 periods.
It's all right. You'll be okay. So, okay, now we want the inverse cosine. So we are going to play the inverse game. We're going to swap inputs and outputs, and we end up with this. Okay, and now y's are my inputs, and so we have the y-axis here. He's up here at +1, down here at -1. My theta axis is now my output axis. Now here's the question. Just like we started at 0 before with sine, I think it's a pretty good place. Let's start with 0 with cosine. And by 0 I mean the output values. Because you'll notice as we're restricting, the thing we're restricting is the range. We're not gonna restrict the input values here. or the old output values. We want to restrict what output values we get, because that's what's messing us up. So I'm going to restrict the output values. If I start here and move down, I guess I could do that, but now we're in negatives, and why don't we start at 0 and move positive? So now, okay, that works. Perfectly good function. Still perfectly good function. Still perfectly good function. Still, uh-oh! It's going to bounce back on itself. And if I go any farther than that right there, then I'll plug in some number here and I'll get more than one output. That's not good. So now I've restricted the range of this thing, and what I have obtained is a perfectly good function. It goes up to pi. Right here is pi over 2. And we could see that, yep, it used to be the case with old cosine that I'd plug in a 0 and get out a 1. Now it's the case that I plug in a 1 and I get out a 0.
Is it called arccos?
Arccos. And I'm going to do the same thing I did right here. In fact, I'm going to go ahead and do that. So, arccos, something like this. Y's are my inputs, thetas are my outputs. He starts here and does this, like that. Here is pi. Here is pi over 2. The biggest input value we could have is 1. The smallest input value we could have is negative 1. Because going beyond that doesn't make any sense. Right? Everybody follow me on that? Like, it doesn't make any sense. So this is theta is the inverse cosine of y, or as I prefer, arccos y. But you're going to see this in your book. Like every other one you have is going to have it written like that. And you're going to need to know that's the inverse cosine, not cosine over 1. Or 1 over cosine, you know what I mean. Not that. Okay? So, okay. There's that. Now, cosine, and I did want to draw cosine here. Okay, here's 1, negative 1, pi over 2. So, like we were playing with earlier, this is y is cosine theta. Here's my theta. Let's say I plug some value into cosine, and out pops a 1/2. Where did it come from? Well, there's infinitely many possibilities, but if you were to ask arccos, where is it going to say it came from?
Pi over 3.
I believe pi over 3. Let's just check that, right? Because 1, 2, root 3. This one is pi over 3. And cosine of pi over 3 is adjacent over hypotenuse. So he would have come, arccosine, as far as he's concerned, he's only going to be looking right here. He's only going to be looking in these first 2 quadrants. And no matter what output you give, he's going to pull it back and say, well, it must have come from right here at pi over 3. And this is what we're seeing right here. This is what this means. If you plug in a 1/2 into this function is going to say, it came right from here, pi over 3. Even though it may have been the case that you actually plugged this one in. Maybe that was the theta you actually plugged in, and the output was 1/2. Maybe it was one way over here. We're here, we're here, we're here. Doesn't matter. As far as arccosine knows, he only knows what's happening between 0 and pi. In other words, this interval right here. This is another wonderful way of thinking about this stuff, is to see it like this and to say, well, if it came from here, arccosine is going to pull it back, and it's going to be somewhere in the second quadrant, right? That kind of stuff. Or this too. They're both very useful to think about. Okay. Okay, we're going to continue with it. So,
Arctan.
So you take any
Arccos.
there are those. There are, and arctan is what we're going to do next, and it will be your best friend for the rest of your life. Arctan is beautiful.
That
You'll
one actually
see why.
goes on with still.
You nailed it. You nailed it. So okay. Actually, yeah, let's just do some examples. All right, I want to leave these guys up. You guys should be sick of this by now. You know what that is. Okay, so just a couple examples to see if you guys are following. So this is 2a. 2a. We want to find arcsine of -1/2.
Well, negative pi over 6.
It should be negative pi, and there's a couple ways we could do this, right? Here's -1/2. By symmetry, this thing's got to be negative pi over 6. And yeah, that is what arcsine is going to pull back. Now, it may have been the case that it came from somewhere else, but we don't know that as far as this is concerned. As far as arcsine is concerned, he's always going to spit out outputs from minus pi over 2 up to pi over 2. If you said that this is 7 pi over 6, you're wrong, because arcsine doesn't know anything about 7 pi over 6. It just doesn't, it doesn't understand it. Okay? Another way of seeing this, we say, okay, here's that. No matter what the original, no matter what the output was -1/2. Arcsine is only going to look and find you this one right here, which, like you've already said, is negative pi over 6, where you could just say, well, hold up, 1 and a 2, I know the triangle that does that, 1, 2, root 3, so for it to be sine, it would have to be that angle. That angle is pi over 6, and we're negative, so we must be in that quadrant right there, and you could also think about that as this guy right here, pi over 6, and so there's that triangle with 1, 2,
There's a lot of ways.
root 3. There are so many ways you could think about that, and so you could say, well, that's either 11 pi over 6, but arcsine doesn't know about that, so he must think he's negative pi over 6. So it's negative pi over 6, and yes, that's the answer. This is negative pi over 6. Okay, next one. Arccos of -√2/2.
So 1 over 2.
That's how I think about it. I certainly immediately say, wait, that's the same thing as -1/√2. It's immediately what goes through my head. So I'm going to go ahead and do it that way. I'm going to say, wait a second. This is what they mean. So you took something, plugged it into cosine, and the output was -1/√2. So it's -1/√2. So which triangle are we working with here?
So it would be negative pi over 4.
The pi over 4 is the only way you're going to get a √2 in there, right? Because of this guy right here. And if they're all pi over 4, right?
Yeah.
So then pi over 4, cosine of pi over 4 will give you the 1/√2. But now we got to figure, well, hold up. Now it's in the negative. And so it must be this guy right here.
So just negative pi over 4. Okay. Or wait.
Is this,
Oh.
is that where negative pi over 4 is? That's pi.
No.
This is pi over 2.
Sorry.
So
3, 5. Wait. 3, 5.
I think 3 pi over 4. The way that I do this in my head is I'm like, well, wait a second. We're in the quadrant between pi over 2 and pi. It's over 4. And so you know that that's pi over 4 right there. It's a wonderful thing about radians. If you're doing this in degrees, get out of here, right? This is so much easier because you say, pi over 4. So 1 pi over 4, 2 pi over 4, it must be 3 pi over 4.
But isn't that bigger than...
Yeah, there's another. The input, though, the input was smaller than 1.
Oh.
Yeah. Yeah, tough stuff. I think he did. I meant to say that, the handoff. Yeah, he most certainly needs to eat. Okay. Okay? See how everything we've talked about is all coming back? And the better you have these in your head, like, the better you'll get all this. So now let's just come back to what you said, right? 3 pi over 4 is certainly bigger than 1. It does not matter, right? Because it's as long as it's one of these. Now you see, now let's look at it this way. You plug something into cosine and out popped negative 1 over square root 2. So you could tell right away, without doing any of that, if you know this picture, that the output of arccos will pull back the angle that's between pi over 2 and pi. And that's what we're seeing right here, right? It's when arccos tries to pull something back, he only goes this far and says, ah, you must have come from there, and it must be the thing that's over 4 between pi over 2 and pi. And you'll notice in every single quadrant, there's only one thing that's over 4, one thing that's over 6, and one thing that's over 3. And if you know that picture that I told you to memorize day 1, this will make your life much, much, much easier if you just have that picture memorized. So if you haven't done it already, memorize that picture. Okay, now, here's the last one we're going to work on before we do more stuff. C is, what is arcsin of 2?
Wait, we can't.
No,
Wait, no.
Oh,
you're right.
Wait, can?
You can't.
You cannot.
It's just not, this does not exist. This says, you plugged something into sine,
And you got it.
and out came a 2. Where did it come from? It never happened.
Yeah.
Go home. It never happened, right? So this does not exist. And you could say 2 is not in the domain of arcsine, if you wanted to be really pedantic. You could say 2 is not in the domain of arcsine. So you can't plug it in. It's like, you know, when we did exponential functions. We took an exponential function, and then we found its inverse by doing the same thing with this exact same paper, right?
Okay.
And we found that it does this, and so now we call this, I guess in this case, we'll just call it natural log x. And so when you say, what's natural log of negative 2? You're saying you plug something into E, and out popped a negative 2. It never happened. That never happened in any world that we're working in.
Yeah.
Right? So, same kind of thing here. Plugging this into 2 makes no sense. I'm sorry, plugging 2 into arcsine makes no sense because 2 is not an output of sine. Okay? Okay. So that was a trick question. That's not actually letter C. I made that up to fool you. Yeah, that's right. Okay, last one. We're going to do 1 period of the tangent function. And this time we're going to do it up this way, because you know what tangent looks like, right? And so, yeah, up that way. Up this way. I'll show you what I'm looking for here. So we're only going to do 1 period, and it's the one that goes through the middle. Tangent starts here, comes up like this, and shoots up. Much easier to draw. This asymptote, where are my asymptotes?
Pi over 2 and negative
2.
And negative pi over 2. Good. Okay, so here's pi over 2. Here's negative pi over 2. Now let's do one extra point. I like to choose this one. I like to choose pi over 4. What is the output?
1/2. Wait, no. Wait. 1 over...
1 over something.
Oh, just 1.
It'd just be 1 over
Just 1 over 1.
It is 1. There we go. It's just a nice point to have. Otherwise, you have no defining characteristics and you have no idea what this thing really looks like, how stretched or how smashed he is. This way we can see how stretched or smashed he is. Now this is theta input, y output, and so this is the graph of y equals tan theta. And what we're going to do is swap the roles of inputs and outputs, just like before. We're going to take our positive y's and make them our new inputs.
We don't have to do anything with this.
Do what?
Well, it's still a function.
It is a function. We don't have to. Well, technically,
We only
we just didn't draw the rest of the function. If we went and drew the rest of the function, then when we flipped it, we would have to choose where to restrict. Although it's pretty obvious which one you're going to choose. Yeah. Like, you know what I'm saying?
The one that's easy to draw.
Like, it's obviously the one you should pick. So we're going to restrict all of the other repeats of this going north and all the repeats of this going south. We're going to restrict the range to be between pi over 2 and negative pi over 2. That's where my asymptotes come in.
And then you can plug in any.
And so, yeah. So let's stop right here and consider what is the domain of arcsin. In other words, what are my allowable inputs to arcsin?
Anything between
Negative
-1 and 1.
1 and 1.
Okay, so what you're telling me is that the domain of arcsin is the interval from -1 up to 1 inclusive.
Yes.
That's what you're telling me. Okay. What about this guy? The domain
Same.
of arccos is the same. We could still plug in -1s up to 1 and we're good to go.
Ranges of signers.
Yeah, let's do the range. What's the range of arcsin?
Pi over 2.
Negative pi over 2 to pi.
Pi over pi.
Are they inclusive?
No.
Yeah.
Yes. Yes.
They are inclusive because you can actually plug in a -1 and you can actually get the negative pi over 2. And this is another, obviously if you're including this in your domain, that should probably be included in your range. And it's not, there's some exotic cases where that may not, and you want to check and see if that does work out. But in general, that is going to be the way it works, right? Like if that's included, that's going to be included. If that's included, that's going to be included. Not always, especially if things get squirrely, like which is going to happen eventually, but actually not in this class. Not in this class. So what is the range of arccos?
Pi to negative. No, just pi to 0.
Pi to 0,
Zero
or
to pi.
as I prefer, in the correct order, 0 to pi, right? Okay? So, all right, now back to arctan. Arctan is your best friend because you never have to worry about this kind of thing happening. Like, you never have to stop and go, wait, can I plug that in? You're going to have to do that with every single one of these. Every time you see an arcsin or an arccosine, you're going to have to stop and go, wait a second, is that bigger than 1? No, that's small, that's small, it's okay, it's good. You never have to worry about it with this. Because no matter what your input is, there is an output to go along with it. And there's only one in this interval, which is really nice. So it used to be the case that I'd plug in a pi over 4 and get out a 1. Now, arctan is the thing that takes a 1 as an input and gives you pi over 4 as an output. We call this theta equals arctan y. It takes ratios as an input and gives you angles back as an output. That's what arctan looks like. Let's get him on the board real quick, and then we'll finish that up. Okay, I'm gonna get rid of this. Pi over 2. Negative pi over 2. Plug in a 1, you get out of pi over 4. this bad boy. Oh, and yeah, we're going to have y's as inputs, thetas as outputs, and we're going to call this theta is arctan y. You could also write it as tangent inverse of y, which is a total pain because it's nothing to do with cotan. But you're going to have to get used to that. That's just one of those things. So let's do this one real quick. No, do domain first. Domain of arctan. All real numbers. Every single real number you could plug in there and get an output. And that output will be between...
Negative pi over 2 and pi over 2.
Okay, so how do I write that as an interval?
Hard bracket.
Hard bracket.
Hard bracket.
Oh, no, soft bracket. Because, yeah.
So, you'll never get there.
Yeah.
You'll never actually get there. You go down to negative 6 billion, it's still not there. Down to negative 6 billion to the 6 billionth, still not there. It's, yeah. So it's from negative pi over 2 exclusive, not including the pi over 2, up to pi over 2. Interesting. The closed interval maps onto a closed interval. Closed interval maps onto a closed interval.
Oh, and that's...
Open interval.
Because it's negative.
Negative
Well, the other one's a
infinity.
segment.
Infinity
But this-
maps onto a open interval. That's not always going to be the case. Functions that do this are very nice. Not every function does it, especially if you have something like this. Like, let's say that that vertex is here at 2. Well, then 2 would be an output, but you'd have the range would be from negative infinity up to 2, close bracket, but the domain would be all real numbers. So what I'm saying is it doesn't always match up. These do, which is nice. Very nice for when you go on to do things. It's very nice that it has this property. But anyway, that's neither here nor there, not for today. So, just something to notice. You will want to know what the range and domain and all of these guys are. But if you have these pictures memorized and you could pull them out in a snap, that'll be good for a quiz, and it'll help you with all of this too. Okay?
Is there a quiz coming up?
Yeah, probably. So, let's move on. Well, I lied earlier and told you that 2c was something that it's actually not. It's actually, what is arctan of negative 1? First off, can we plug in a negative 1 to arctan?
Yeah.
Of course, plug in anything to arctan. That's the great thing. What's it going to pull back?
Pi over negative pi over.
Negative pi over 4. And this is, you know, you could just straight up use symmetry here. Though we have, I would suggest you don't, because we haven't really talked about it. It is symmetric, and it does have this property. But, and I guess, I mean, if you could prove that it's an odd function, you're good to go. But it's better to think, like, okay, we have our tan function, and it actually goes on forever and ever in both directions. And somebody plugged in a number somewhere, and out popped negative 1 as an output. Maybe it came from over here. Maybe it was this one. Somebody plugged in this value right here, and then it got pushed forward and popped out a negative 1. Now we want to pull it back using arctan. Well, arctan doesn't know anything about that stuff. He's just going to look and pull him back and say, okay, you pull back to here, whatever that value is. And as you've already said, it's negative pi over 4. I'm not going to go into that. You should get that by now. Okay? Now, okay, moving on. Now we're going to do a bunch of examples. So, I do want to leave these guys up here for now. Questions before we start just hitting examples? Okay. All right, so here we go. 6a arcsine of pi over 2?
Oh, it's like,
Arcsin is that. So.
that's gonna be 1/2. Wait, no. No, what could it?
Oh wait, you plug in a pi over
Yeah, you
2.
plug
So that's
Plug
bigger
in
than 1.
a pi over 2.
one.
So can we do it?
No.
No! Yeah, it's so tricky, right? And you think, well, there's the pi over 2. But wait, then there's the input and the out. But this is the input of the output, and the output has become the input. Oh, it's so tricky, right? So whenever you see arcsine or sine inverse or anything like that, the first question in your head needs to be, is that bigger than 1? And it turns out that, yeah, pi over 2 is bigger than 1. So you could say, if you want to be really pedantic, pi over 2 is not in the domain of arcsine.
Call it undefined or.
Yeah, arcus? Yeah, whatever. Or you could say undefined. Undefined is perfectly good. I'm not sure what the book says about these. It's probably undefined. But it's simple. You cannot do this. Because that says that you plugged something into sine and out popped pi over 2. That never happened in the history of the world. So, number 8, A, is sine of arcsine of
Oh, no.
2/3.
Sine of x. Oh, so it's just 2/3.
So,
It should just be 2/3. The thing that you're going to need to check here, though, is can I do this? Can I plug
Oh.
2/3 into sine? I mean, into arcsine?
no.
Yeah.
Yes.
Yeah, 2/3 lives right here.
Yeah.
And so this is what goes through my head. This is what goes through my head. There's a couple different pictures that go through my head with this one. One is this. Does 2/3 live here? Yeah. And so there's going to pop out some angle, whatever it is. Then I'm going to take that angle, plug it into sine, and it's just going to bring me right back to where I started, at 2/3. Another way of seeing it is to start here with sine. And since we're talking about arcsine, I know that ultimately all I really care about is what's going on between here and here. But at any rate, this means that you plug something into sine and got out a 2/3. And I could say, okay, then arcsine's going to pull it back to give you the angle that it is. So in other words, this is the same thing as sine of that very angle. That angle that gives you out 2/3. Well, then plug it in, and it gives you 2/3, right? But you do need to kind of do this waltz in your head and say, well, does this work? Because as we see, sometimes they give you stuff that just does not work. And so you have to start and say, well, wait a second. And like, this is going to be a big thing. We're going to see this in just a minute. Very helpful in a lot of this is to just start by rewriting this. Anytime you see arcsine or arccosine or arctan or inverse tan or inverse cosine, any of those, rewrite that as theta. Right now, it's not so bad. In a minute, you probably want to rewrite it as theta. So okay, yes. When this is in the domain of this, then this is always going to pop out. Okay? That's always going to be the case. The problem's going to be, well, there's a few problems, and we'll see in just a second. So, okay. Okay. Man, I really don't want to get rid of these. I can get rid of the domains. Alright. So, 8C. What's that?
Is that 9?
Negative 9.
Should be -9. Well, let's just think. Can I plug -9 into arctan?
Yeah.
Sure, you plug anything into arctan. It'll come out over here. There's -9. Gives you some angle down here in the negatives. And when you plug it right back in, it's going to come right back to where it came from, right? So, another way of saying, okay, -9 was my output of tangent. And so when I pull it back, it pulls me back some angle theta. This is that angle theta. That is that angle theta. Because look at how I've written this. Theta equals the arctan stuff, right? So this is some angle, And it happens to have the property that when you plug it in, it gives you -9. Well, if you plug it in, it gives you -9, right? The thing to check is that the domains are good. That you're not plugging in something that doesn't fit into here for these. Okay. That was that. Now things get tricky. As if it weren't tricky. No. Okay. 12b. We want to find what is arccos of cosine 5 pi over 4. Do you think 5 pi over 4? Right?
Oh, but
Oh,
Wait,
no!
we can't-
Can 5 pi over 4 be an output of this guy?
No.
No. So let's look at what's going on here. Let's look at what's going on. This says we're going to start with that angle.
so you have to like.
Okay, here's pi. Here's 5 pi over 4. We're going to take 5 pi over 4 and plug it in to cosine. And he gets pushed forward to give me some output. Now, what arccos is going to do is look at that output, whatever it happens to be, and then say, well, and since it's over 4, I guess it's easy to figure out. It's 1 over square, negative 1 over square root of 2, right?
Yeah.
Because let's look at this. 4 pi over 4, this would be 5 pi over 4. The reference angle is pi over 4, so that's a 1 root 2, right? So then adjacent, which would be -1 over that guy, -1 over root 2, so yeah, it's -1 over root 2. Well, arccos doesn't know anything beyond here. Arccos only knows what's happening between 0 and pi over 2, so we have to say, aha, as far as arccos is concerned, he's going to take this, pull him back to here, and find this angle right there, which is what? We know it's over 4. It has to be over 4.
Just pi. Wait, 3 pi over 4.
Yeah, because it's the one that's between these two. So he's going to pull back this one right here and say, ah, you must have been 3 pi over 4. And so that's your answer right there. Oh man, yeah. So that's so tricky. The answer to this is indeed 3 pi.
Can you just minus pi is over 2 until it. Or pi is over. Yeah, pi is over 2 until it fits into.
No, because let's look. This is that distance right there. And if we bring that back by pi over 2, 1, 2, gives you that distance. Yeah, it might work. So if you look in your book, there's a very nifty way that they have a thing about that. It's like, it's this minus this. I don't even look at that. That will mess me up every time. You could look at it. You could go down that dark road if you want. I choose not to even think about it. I would much rather do it this way. If you want to try it a different way, that's perfectly fine. If it makes more sense to you, I suggest that you read the book and see which you like more. And I think this is actually, this kind of stuff is in the earlier section that we skipped from chapter 6. This is, by the way, chapter 7. 6.5 or something like that. I think it's in there. They have nifty ways of just calculating. It's like, it's either this one or this one. So you either take pi and subtract it, or you take pi and add it. And it's like, okay, that's cool. I'd rather use a picture. Because now I can see, well, it has to be over 4. To get this output, your triangle must have been pi over 4. That's the only way you get this output from cosine. And knowing that it must have come from here, well, I know that I'm between these. Or, right, you could say, well, yeah, it would be here. And so the output would be somewhere between pi over 2 and pi. Right? We already did this one. So, couple different ways of doing it, and knowing that, okay, it has to be over 4, and it's between pi over 2 and pi, well, I just did that right here. Right, here's pi over 2. Here's pi. The thing that's over 4 must be 1, 2, 3 pi over 4. Like that. Questions?
Would it be possible to have arc cosine of like tan?
Are you reading? Are you reading my notes? Okay, I just said things are about to get more tricky. They're about to get way more tricky right now. And this is going to be the most difficult thing. I think there's only 1 or 2 questions in your homework that are actually like this. But this is by far the most difficult.
Arc cosine.
Yeah, so here we go. 16b. This is 16b. And it is compute secant of arctan 7/4.
I'm right about this is easy.
First off, is this possible? Can I plug that into that
Yeah,
guy?
you can plug
You
it.
absolutely, you could plug anything into arctan. So this is where I suggested that we do this. Okay. Whenever it's not simple, like you have sine of arcsin, or arcsine of sine and stuff like that, then you might be able to get away without doing this. Whenever it's something else, I suggest that your first step is to do this. Let theta equal that thing. Okay? Because we want to get back into the headspace of angles. Okay? Right now, that thing, right, it represents an angle. Remember how we got this. We flipped it over and we said you plug in some angle theta, blah, 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 blah. This is the inverse of that, right? This is the thing that gives you that angle. And so this thing itself is that. But what does that mean? Now let's just think about originally the tan function. Right? It comes up like this, comes down like that. There is some input, not sure where it is exactly, but there is some angle theta that gives me 7/4 as an output. That's what this is, right? You're plugging in 7/4 into arctan, and out pops some value theta. That's what this is. We're calling it. That's theta. That's the same guy. That guy and that guy are the same guy, because this is the same piece of paper that we just flipped over, right? So, like, this thing is an angle. But now let's look at this. What did I just say? That there's some angle theta, so that when you compute tangent of theta, so what does this mean? This means that tangent of theta is 7/4. Everybody follow that? You know, it's kind of like if I had this, like x equals square root of 7/4. I could then undo both sides, right? Because this is the inverse of some function. What function is it the inverse of? Well, when you square it, square that, and you get 7/4. That's what I've done right here.
Yeah.
I've taken the inverse of the inverse,
So you
right? Or I've pushed it forward. Is another way.
tan of both sides, I guess.
That's exactly what I did. I took tan of both sides, and let's be explicit about that. That's what I'm, because that's how you undo arctan. You push it forward. So you say, this is the same thing as tan of inverse tan of. And the nice thing about tangent, about arctangent, is that you never have to worry about doing this. Whereas with the other ones, you're like, wait, hold up, wait, does that work? You could just do it blindly with arctan. And so the inverse of the thing, so you take the inverse, then you push it right back, and it just comes to where it started off from, right? So that's what that means, okay? That's explicitly what I'm doing when I jump from this step to this step, right here. I'm explicitly taking tangent of both sides, right? So you take tangent of theta, and you get, tan theta. You take tangent of arctan, blah, 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 blah. It just makes whatever that stuff was pop back out.
Yeah.
So one last time, just to be perfectly clear. You take 7/4 and plug it into arctan. which is what this is. Right, I'm looking at the innermost thing. It says you take 7/4 and plug it into arctan. Okay, what pops out? Well, an angle pops out. Which angle? I don't know, but it's between 0 and pi over 2. Some angle between 0 and pi over 2 pops out. It's the same thing as saying you had some output from tangent that was 7/4. It must have come from some theta that's between 0 and pi over 2. That's what we're saying. So let's give that guy a name. Let's give that angle a name, theta. That's what we've done. Now, it happens to be that that very theta, if you were to plug it into tangent, would pop you out 7/4. Right? That's what that means. So, now that we know that, can we construct a triangle where tan theta equals 7/4?
Yeah, we need a side with 7. We need the opposite side 7.
Yeah, so let's just do this. And where does 7 go and where does the 4 go?
Opposite 7 goes opposite.
And the 4 goes
Adjacent.
adjacent. Which means that guy's what?
16. The square root of 16 plus 49. Whatever that is.
I have root 65.
Yeah.
Okay? Everybody, you better know how I got that. Okay? This guy is root 65. So, now my problem reduces to just being, this is the same thing as just what's secant theta. With that triangle, that very triangle. What is secant of theta?
It's just root 65 over 4.
Yeah, there you go. Root 65 over 4. And that's your answer.
Not too bad.
It's not too bad. There's so many things you get tripped up on, especially like domain problems here, making sure that that's the case. But the most valuable thing you could do is whenever you see one of these, unless it's completely obvious, like you have sine of arcsin or whatever, is just replace this symbol with theta. That's why I painstakingly wrote so many times on the board, cosine of the thing is the angle. That this symbol represents some angle theta. This symbol represents some angle theta. Remember how we got these guys in the first place. We started off by taking theta, an angle, as an input, and we did some magic to it, and blah, blah, blah. That means that the output of this new thing is an angle. And so it will behoove you to be able to identify where in this crazy equation, in this case, it's not an equation, it's just to compute this. You can say, which part of this is the angle? Well, it's not the secant part. And usually if that part's on the outside, it's usually this type of thing, where it's on the inside, and you say, well, hold up, wait a second. And especially when I see this, I don't know what to do. I'm like, wait, tangent, secant. And then you start to get creative, and you're like, well, maybe, since that one's cosine, this one's just sine over, because maybe I take a cosine and a sine, and no, just say, wait, what is this? This thing is an angle, so you just need to find secant theta. That's it, right? Then you do your hard stuff. You go out. But the problem itself becomes much easier. Because now you're like, okay, I have a goal. And if I could get information about this angle theta, then I could solve this. And the information's tied up right here. Right? You know that if tangent theta is this, well then it must be this triangle. Right here. Right? Or, I mean, you could, if you really, really want to, you could divide every side. 65, so that you end up with this triangle, and then technically, yes, it's on the unit circle. It's a point on the unit circle. You could, but yeah, that's the idea. Questions?
We're gonna do the arcsecants.
No, they exist. Like you can do them, and it's the same thing, right? You draw the thing, flip it over, decide where are we going to cut off, and you'll never see those again. Like outside of this book, you will never see arcsecant or arccotangent or arccosecant. You'll never see them. You only see these three. And that's really all you need, you know. And so, I can't think of, yeah, we're a little over. Okay, so just one more thing I did right. Please, like, explicitly write this somewhere, especially as you're first starting these. I want to see this. Like, please don't jump from here to say here, or from here to not having any of this and then writing all this other stuff, because that's going to be hard for me. I would like to see your explicit substitution written somewhere.